Good morning, ladies and gentlemen. I am David Williams. I am Professor of Biomaterials here at WFirm, and it is my pleasure to introduce this session on essential biomaterials science. And I'll do so by covering basic elementary material science, leading through to the specifications and selection of biomaterials for various forms of medical technology. I've been in this field for quite a long time. Most significantly, I was the editor-in-chief of the world-leading journal Biomaterials for over 15 years, and also global president of the Tissue Engineering and Regenerative Medicine International Society. So my perspectives are both local, national, and international, and hopefully that will come over in this short presentation. I want to start by talking of the challenge facing us with the design and application of materials in tissue engineering and other forms of regenerative medicine. A few years ago, I organized a conference in Xi'an in China, which attempted to address some of the major stumbling blocks, the holding aspects of our approach to tissue engineering, regenerative medicine, and their translation into clinical practice. And in the blurb of the publication coming from that conference, I gave the following statement. You'll see it on the slide at the top, but let me read this so you can understand my position here. In general, we cannot regenerate those parts of our bodies that have fallen asunder. Whereas a newt or salamander can regrow limbs at will, our own pathetic attempts usually end with functionally useless scar. Of course, we would all rather have the brain of a human than that of a newt, and our evolutionary pathway determined that we were better off with good brains than regeneration. But the question arises, if we are now so smart, then why can't we engineer nature to equip ourselves just now and then with that regenerative power of a newt? That is an essential part of our challenge. We need to define some of our terms, and you'll see me doing that a few times in this presentation. I defined tissue engineering over 15 years ago, and you see in the center of the slide, where I said that the creation of new tissue for the therapeutic reconstruction of the human body by the deliberate and controlled stimulation of selected target cells through a systematic combination of molecular and mechanical signals. I emphasize a few points there. This is not an accidental regeneration of tissue. This refers to a controlled process where we are stimulating selected target cells. They could be stem cells, they could be adult cells, but through a systematic combination of molecular and mechanical signals. A couple of years ago, I helped to organize another conference in China concerned with definitions in biomaterials, and that was in Chengdu. And here, that conference decided on a slightly simplified version of that definition, which you see here. It is the use of cells, biomaterials, and suitable molecular or physical factors, alone or in combination, to repair or replace tissue to improve clinical outcomes. Whichever way you look at it, biomaterials are at the center of tissue engineering processes. The challenge, therefore, with materials in medical technologies can be summarized in this slide. We have a disease, a defect, or maybe an injury. If we have lost mechanical or physical function, we may replace that tissue with a medical device. I emphasize mechanical or physical function. In some situations, the loss of certain tissues or organs may be remedied by the use of transplantation. But in the blue, when the loss of function is biological or physiological, devices are not usually applicable and organs for transplants are scarce. We then attempt regenerative technologies such as tissue engineering, and those attempts are really at the heart of this course this week. And we have to consider where materials, and specifically biomaterials, are relevant. And the little dotted lines say that, yes, materials may be used in medical devices, To some extent, materials are used in transplantation, but not a great deal, although they may in the future. And then in tissue engineering, how and where are biomaterials relevant to those technologies of tissue engineering? Critical to this are the nature of those diseases or injuries or conditions where tissue engineering is likely to be most relevant and most urgently needed. And at the top of the slide, I give a few pictures of the diabetic foot ulcer, looking horrendous as it is. And I refer to this as being the unmet clinical need. And the question is, can that be treated by an implantable device or drug? Basically, no. Can we use transplantation? Not at this point. Is it an opportunity for tissue engineering? And then what materials are required in a tissue engineering product here? We've still got some ways to go, but this represents, I think, the goal of tissue engineering, unmet clinical need. I have to say there are many conditions in the body where medical devices do produce very good performance, whether that is in joint replacement, prosthetic heart valves, artificial arteries, intraocular lenses. We can get very good performance. But in many situations, such as the one in this slide, such as those involved in degenerative diseases, such as Alzheimer's, Parkinson's, diseases and injuries of the spine, we are not there yet. And that, to me, is where our attention should be placed. If you want to have more details of the material science I'm referring to in this lecture, I published a textbook a few years back by Cambridge University Press, Essential Biomaterial Science, which is fairly easily available. But I suggest you have a look at that if you want more details. So in relation to definitions, we have to start with biomaterials. What are they? And I published a paper in the Journal of Biomaterials back in 2009 on the nature of biomaterials, in which I defined a biomaterial as being a substance that has been engineered to take a form which is used to direct, by control of interactions with components of living systems, the course of any therapeutic or diagnostic procedure. This paper, the leading opinion paper, was forward-looking, looking towards the situation where biomaterials were used not just in the replacement of parts of the body, but in other therapeutic and diagnostic procedures, and where the performance was determined, as you see there, by the control of interactions with components of living systems. And that's a far cry from the ideas we had of biomaterials a couple of decades ago. As implied, there are many procedures in medical technology that we can possibly use, which you see in the blue low down. And what are the products that we use there? Well, materials themselves, there are very many which we use on industrial scale, domestically and elsewhere. In this slide is a combination, and just to run through a few of these, top left, I indicate here a piece of acrylic used in furniture, a thermoplastic polymer, polyether ether ketone or PEEK, a very, very good engineering material. Here we have a polyester, Dacron, used in clothing. The yellow at the top right, polypropylene fiber. Middle left, high performance alloys in engineering. The lovely purple in the middle, that is silk. And across the right, some molecules of polyethylene glycol and hyaluronic acid used in pharmaceutical preparations maybe, and other applications. The black stuff is alginate, derived from seaweed. In the middle, chitin and chitosan materials derived from various forms of sea life. And to the right, high performance aluminum oxide. And lower left, gold, platinum alloys, and the bicycle with a large amount of titanium. Those are materials that we have developed in material science over the last several decades, indeed half century, for use in many, many applications. The reality is that when we come to look at common biomaterials, they are essentially the same. Modified, optimized may be, but the top left here, that is still acrylic, used in intraocular lenses. That's the PEEK material used in spinal reconstruction, Dacron for artificial arteries, polypropylene as a mesh in hernia incontinence repair. Here are alginate microcapsules used for encapsulating cells. Here we have silk as a scaffold material. That PEG we saw before, again in pharmaceuticals as a fairly sophisticated molecule. And across here, some chitosan used as a scaffold. High performance alloys in joint replacements. Here a cobalt-based alloy. In the middle here we have gold nanoparticles used as contrast agents. Lower down, very, very high performance, very, very good aluminum oxide used in joints. Titanium for dental implants, platinum, iridium alloys in pacemaker leads, and down here some more chitosan in nerve tissue engineering. So most of our biomaterials today have been with us for 20 or 30 years, and they are derivatives of common engineering materials. And we need to bear that in mind as to what we're trying to look for in the future. When looking at those materials, there are many ways we can classify them. The simplest way is to look at them in 6 different classes of metals, ceramics, polymers, carbons, composites, and especially of relevance in tissue engineering, engineered biological materials. There are many such materials in each of these groups, which I don't have time to discuss today, but we will be emphasizing polymeric systems where we have some synthetic thermoplastics, synthetic elastomers and textiles, but especially some naturally occurring hydrogels derived from biopolymers. And in tissue engineering and other forms of regenerative medicine, we are tending to base our new materials on one or other of these forms. So what are we looking for in a tissue engineering biomaterial? What guides our selection? Well, strength is going to be important. Obviously, a biomaterial used here cannot be too weak, but this is not a major factor. Mechanically, probably the most important is this question of elasticity, and especially the elastic modulus, which does control cell behavior on their surface. Physical properties, the optical, electromagnetic properties, occasionally relevant, but not usually. Biostability is very, very important in many situations because usually we want the material to be degradable. Not always, but usually you would like it to be degraded as tissue is being regenerated around it. We certainly want a lack of toxicity, that's very fundamental. And yes, we want to have biocompatibility, which I'll be addressing in the next few slides. But remember this, since tissue engineering involves, as I said before, that deliberate and controlled stimulation of selected target cells through a systematic combination of molecular and mechanical signals, the biomaterial should be able to deliver those molecular and mechanical signals. The biomaterial is not there just as a support system. It has to be actively involved in delivery of those signals. So I mentioned biocompatibility, and what is that? Most of the world refers to biocompatibility and its definitions in terms of the Williams definition, which was originally derived way back in about 1985, and the conference in Chengdu just a couple of years ago confirmed that that is still the most acceptable definition. So biocompatibility is the ability of a material to perform with an appropriate host response in a specific application. This tells us the material has to perform and not simply exist, and we have to have an appropriate host response which depends upon the application. And the full details of that definition and the mechanisms involved were published by myself on the mechanisms of biocompatibility, again back in 2008, and subsequent papers. Now bear in mind, in the green in the middle, this is very, very important. For most implantable medical devices, the most appropriate host response is no response. The biomaterial should perform and continue to perform the required function without inducing any adverse response, and that is usually achieved by maximal inertness. It is of no surprise that the materials we use in those devices I mentioned, the hip replacements, heart valves, and so on, are all based upon the most inert metals, carbons, polymers, and ceramics. Full stop, period. However, with tissue engineering applications, if there is no host response, as in a medical device, if there's no host response, there'll be no tissue regeneration. Here, the most appropriate response is involved with interactions that deliver those molecular and mechanical signals. And our continued use of inert materials as tissue engineering biomaterials is the most important failure mechanism in tissue engineering, in my opinion. Nobody agrees with me, but that's certainly my position. Now, that conventional definition of biocompatibility is good, it's conceptual, but it doesn't give us many mechanistic insights associated with interpretation. And it has to be said that classical views of biocompatibility have failed to predict significant adverse effects attributable to implants. In vitro data is not the same as in vivo data, and it's very, very difficult to translate that into clinical experience in humans. Traditional views of biocompatibility do not allow for the idiosyncratic nature of human responses to external stimuli. That's hugely important. And they do not reflect the influence of the local and systemic conditions of the host. These views, the previous views, do not adequately reflect the fact that biocompatibility is not a property of a material, it is a property of a biomaterial host system. Probably the most important sentence I can give you today. Biocompatibility is not a property of a material, but of the material host system, whether as a material in the tissues of the body, a material in contact with cells in culture, in a bioreactor or whatever. And hence, there is no such thing as a biocompatible material. I've published that several times. There aren't many people who like me saying that, because everybody talks about their biocompatible material, the wonderful new biocompatible material. There is no such thing. You may have good biocompatibility under one condition, but that's not relevant anywhere else. And that is a big, big problem for us. I'm not going to go into this at all. This slide here is complex, but to emphasize that when we have a biomaterial of any size or shape in any biological situation, there are three areas which we have to consider in terms of the contact with the physiological compartment. Adsorption of macromolecules, particularly proteins, the perturbation of the mechanical environment, and the perturbation of the physiological environment. And looking at all of the examples of biomaterials and tissues, we can identify a number of pathways with which the biomaterial interacts with tissues. Simple, complex, but biological pathways. These are not new. Biomaterials have not generated new pathways, but they involve biological pathways which have been known for some time. And this paper was published just a few years ago, showing when biomaterials are in contact with tissues, there are usually identifiable pathways by which the interactions take place. And again, those details are encompassed in the publications I've mentioned. So moving on to tissue engineering biomaterials at the last stage here, this slide says tissue engineering templates. A few people may have heard me say this before. I do not like the universal term scaffold. A scaffold is a structure used outside a building, an engineering building, which helps the building to be put up, but then the scaffold is thrown away at the end. Tissue engineering materials are not thrown away. They should be taking part in the formation of new tissue. And therefore, I like the word, prefer the word template. That's what we're using. And in order to achieve spatial temporal control over that tissue engineering process, we need biomaterials that can be formed into a suitable template. It may be preformed, injectable, or printable. It may have in situ gelling or setting, have the appropriate mechanical and biophysical properties, which will change during that setting process maybe, can incorporate and release the necessary specific biomolecules for that aspect of tissue regeneration, degrades with the appropriate kinetics and lack of toxicity, and has all the appropriate biocompatibility characteristics. That is what we're looking for if we want spatial temporal control over cell behavior. But bear in mind, the biomaterial alone cannot perform all these functions. It needs to be in a form that has appropriate architecture and morphology, and needs to convey and deliver relevant biomolecules. So, in my opinion, a tissue engineering template is comprised of a biomaterial, its architecture, which could include nanoarchitecture, and biomolecules. And very importantly, this template has to simulate the cell niche. Very, very important. We have to consider when we have a template or classically a scaffold, does the environment of that scaffold replicate what a cell encompasses? Classical solid free-form fabrication of polymers and ceramics, an old slide here, obviously, but you have to look at that structure by classical forming processes. Does that microstructure seem to you to represent a typical cell niche? And the answer has to be no. We have to do an awful lot better than that. And I have to say, aspects of printing and technology now are moving in that direction, because classical structures will not provide us with that environment. So our specifications, the material should be capable of recapitulating the architecture of the niche of the target cells, whatever they are. And very importantly, that cell niche is changeable over time, especially if we're looking at stem cells, for example. And the material should be, it's a big ask, but should be capable of adapting to the constantly changing microenvironment. The material should have elastic properties, particularly stiffness, that favor the mechanical signaling to those target cells to optimize differentiation, proliferation, gene expression, and so on. That stiffness is clearly of huge importance. And perhaps in situations we have to have optimal surface or interfacial energy characteristics that facilitates cell adhesion and function. There are many optional specifications. I just include some here. The material should be degradable if that is desired. It should be injectable or printable if that is desired. And where necessary, and this is becoming very important as we look towards more personalized approach to tissue engineering, the material should be compatible with the processing techniques that simultaneously pattern both the materials and living cells. What are we using presently? Well, we do have some porous solids. Many of them are porous synthetic polymers. More often than not, we have hybrid structures. For example, a blend of synthetic polymers, such as PHB and natural, silk, elastic, and so on. Hydrogels, and especially engineered peptide hydrogels. And Sanjin Lee will be talking about some of these hydrogels and printing a little later. And of particular interest to many people, decellularized ECM materials. And in red at the bottom, it's not an aside, it's a very important point, that standard biodegradable synthetic polymers prepared by standard fabrication routes are unlikely to provide optimal tissue engineering templates. And prior FDA approval of materials used in medical devices is not an appropriate specification for a template. To say that a material has FDA approval for use in a suture or other simple medical device is not appropriate for us at this time as we move forward. I mentioned cell printing. This is, and again, you'll hear a few presentations on 3D bioprinting. A very, very interesting, appropriate way forward of printing both cells and materials to get, especially in personalized medicine, the structures that we need. Let me move over that in a view of time. I mentioned the conference back in Chengdu, and you may have appreciated that definitions are very important to me. It's worth looking at this, these definitions published by Elsevier a couple of years ago, because these definitions and all of the discussion leading to these definitions is contained within this small book. This deciding on definitions of regenerative medicine, responsive biomaterials, tissue-inducing biomaterials, bioinks, organ ownership, and so on. And I do emphasize this is very important for you to look at these definitions if we are to have a common language. So that, ladies and gentlemen, is a brief overview of the specifications and the process of selecting biomaterials for tissue engineering. If you want to contact me, you'll see my email at the bottom down there. Now, clearly with a presentation pre-recorded like this, I have no idea what people are thinking about my presentation. I normally like to be very dynamic, interacting with audiences. That's not possible with this. There will be a small amount of time at the end of this session to have some questions if necessary, but please contact me if you want to agree with me or disagree with me on any of those aspects. Thank you very much. Where will stop?